So I'm Michael, this is Shu here. We both worked on low-level JavaScript. And I guess it's a programming language, right? It's not the world's most beautiful programming language. It's still JavaScript, however, so a low-level JavaScript, well, a JavaScript program will just parse as a low-level JavaScript program. So you can essentially, it's just JavaScript with some type annotations. And what is it for? What's it good for? Well, it's only, the real purpose of it is to let you write sort of memory-efficient code in JavaScript, a little less painfully. And of course, it compiles to JavaScript. So here's my favorite data structure that I learned when I started computer science. It's a linked list. So can anyone see the code? All right. So this is how I would write a linked list in JavaScript. Now, if you wanted to create, say, a linked list of 40 million JavaScript objects, which is quite impressive that you can do it so quickly, it takes about 2 to 4 seconds in either SpiderMonkey or in V8, which is pretty good. But if you actually look at what's going on here, is the JavaScript, every individual JavaScript object is quite fat, right? It has a header, which contains some sort of a type information, either pointed to the prototype or some data structure that maintains this information about the object. Perhaps some GC flags. It has several properties in it. So in the linked list example, we were only using 2 properties. But it may be that the object, when it was first created, had more properties in it, perhaps slots to hold at least 4 properties, because objects are extensible. And each individual property within the object could sometimes be up to 8 bytes long, right? Because you can either store int, a double, perhaps a reference. So they're quite fat. So if you look at what this looks like in memory, you just end up with these very fat sort of JavaScript objects, and you can represent this much more efficiently with using some sort of an array data structure, right? So you can just allocate little nodes within the array, and then you can treat pointers as offsets within the array, and you do some like really ugly JavaScript code to sort of manipulate this data structure. Now, you can do this very efficiently. So one thing we learned from mscripting is that using typed arrays, you can actually model memory pretty efficiently. So I guess I don't have to explain typed arrays. But essentially, just real quick, just allow you to overlay different views on an array buffer. So essentially, the way LLJS works, you sort of request a memory module, it allocates, say you want 32 megabytes or so, and then it gives you the ability to read and write in this array buffer using these views. Now, okay, so the previous example, if you want to write it in C-like way, you'd basically write this kind of JavaScript. So here you'd essentially just like P, it's a pointer to the first object, and the P last is an index to the last object in the array list, into the int32 array, and then you do some like manual pointer assignments and so on. Now, if you run this kind of code in SpiderMonkey or in V8, it's about 10 times faster than the previous example. So which is quite a big difference. Now, this is obviously for several reasons. But what is more interesting is the memory usage. So I used a dtrace probe to sort of measure the amount of memory that's requested from the operating system by both SpiderMonkey and V8. And in the example with objects, it's about 2.4 gigabytes, right? The actual amount of data that we really need is only about 300 megabytes, right? But the amount of sort of memory requested is much, much larger. So it's about 8.24 times in SpiderMonkey. And in V8, it's about 13 or so. Now, this is virtual memory, so I'm not saying the engines really use this much memory, but it's still quite significant. If you were to program the same thing using structs, you would end up with only about a 1.3x sort of memory overhead. So in either case, both like the difference between using objects and structs is about 8x, somewhere between 4 and 8x, which is quite significant, I think. So basically what we wanted to do is like, can you just write this kind of code in JavaScript? And I understand it's extremely ugly. It's just C pointers and arrows and stuff, right? But it kind of fits into the syntax. Really all you need to do is just sort of add these like C-style type annotations in front of variable declarations. Okay, so we sort of tweeted about this. We worked on it for like 3 weeks, tweeted, and then could you imagine like the tweets, right? So what have we done? The world just wrapped around and swallowed its own tail. This is my favorite. Sometimes you just want to tell people, please, just instead of doing this, go volunteer at soup kitchen or something. And I totally agree. It's crazy, crazy. All right, so how does this all get started? Well, when I was working on Broadway.js, I was really surprised with the fact that like you can actually write a codec in JavaScript, and without any sort of like interruptions. I mean, the frames were like, I mean, it was not as efficient, obviously, as C, but you had no GC pauses, which was kind of really important for doing that kind of programming. So we sort of looked at mscript and said, can we just take sort of the good parts of mscript? And I mean, it's great, but it still relies on a C and C++ toolchain. So if you actually want to integrate, write some code like this in your JavaScript programs, you have to rely on the C and C++ toolchain, and then use LLVM and compile it to JavaScript. So can we just sort of, why not just take the C and JavaScript and add them together? And we came up with LLJS. This is sort of, well, originally the name was star.js, but then everyone complained that they couldn't Google it. So we changed it like the next day. All right. So what do you really get? Well, the first thing you get is there's no more var statements. It just lets, right? This is sort of to make it look more like, you know, C, C#, Java, and so on. Block scoping. You get machine types. So if you declare a variable y, which is the maximum integer size, and you add 1 to it, you don't get sort of overflow into a double. You just end up with 0. You can declare structs, like you would expect in C and C basically. Well, sort of C-ish with declaring your functions within the struct. And here what we've done is we've overridden this sort of to mean a pointer to the vector struct rather than JavaScript does. But so essentially this is what this looks like, right? You can have constructors. This is a much more efficient representation. It only takes about 8 bytes, right, for the 2 floats. And property access is a lot faster because when you say something like car.velocity.x, you don't have to do pointer chasing to get the objects and then request properties. You just compute an offset into the car sort of data structure. We also have arrays, like C arrays, multidimensional. You can just compute offsets into them very quickly. Unions. Some people also wanted these bit fields that people do in C. I actually didn't even know this was possible, but so I guess we'll try and see if we can do that as well. Of course, you also have pointers. So declaring code like this when you say you have a swap function, takes 2 pointers. So you can do all this weird C pointers. You can also take addresses of local variables, right? So the way, how do we implement this, right? You can't get an address to a JavaScript thing. So if at any point you take an address of a reference, of a JavaScript object, well, variable, we just allocate on a stack. So we emulate a stack using this SP variable. We decrement it. I don't know if the mouse works, but so this would be like a method activation frame. We just subtract the stack pointer, and then we allocate X variable at the first stack location, and then the next one at the following one. You can do stack and heap allocation of structs. So you can, for example, write code like let vector v0, and then you can call a constructor. And this, so by the way, on the right-hand side, okay, on your right, it's what we compile to, and on the left is LLJS code. So you can declare, for example, 2 vectors on the stack. And if you want to assign one vector to another, since these are value types, we just emit a memcopy operation. Of course, you can also declare, you can allocate things on a heap. So you can say new vector. So here, new means something else. Because we know what the type of vector is. It's a struct type. Then we just emit a malloc followed by a call to the constructor. The delete operator is also overridden to mean something else. In this case, it calls free on the allocated address. Of course, this means you have to implement your own malloc and free. And we have. I read the C KNR book, and I tried to understand how malloc, like, we just copied exactly the same implementation of malloc and pasted it in LLJS, and more or less worked. All right, so I think this is Shu's. So Shu's going to talk about sort of the more implementation details.
Hello? Hello? It's on? Great. All right, so I'm going to talk more about the implementation side and the compiler. So what do we get with kind of emulating the heap using a giant typed array? Well, among other things, we get safety, in quotes. Since we have the entire memory in a typed array, it means we cannot get crashes in the traditional sense, like if you read out of bounds or something that your program crashes. Basically, all you get here is, well, you get your program probably just has a bug because you're reading memory that you didn't intend to. But this allows us to basically have the C type system and lets you do unchecked casts and memory operations. They are unchecked, and everything's a reinterpret cast. Like in the bottom here, you can cast anything to a pointer. There's really no complaints, but you're not going to get any crashes. The compiler itself is fairly straightforward. We've used several very useful open source tools like Esprima and ESCogen to hook into basically a couple transformation passes. But most of the stuff we use is available to the web. We extend Esprima with the ability to parse type annotations and some other C constructs. Then we run a couple transformation passes, and then we pass it off to ESCogen to serialize to JavaScript. If any of you has had the misfortune of writing a C front end, you will know that cast expressions are a pain in the ass to deal with because they are ambiguous between function calls and cast expressions. You don't really know until you have parsed the entire program what is a function and what's a type. And yeah, that's just a little aside. That not everything in C is nice and clean and simple. So what do pointers compile down to in LLJS? On the left column, the leftmost column, you see LLJS code. In the middle column, you see LLJS generated JavaScript. And in the rightmost column, you see Emscripten generated JavaScript. So basically, we have 3 pointers of varying sizes. The I means that it's signed, and the 32 means how many bits it has, and then 16 and 8 and so forth. And then we assign them to each other, and we do some dereferences. Now, typed arrays, as you know, allow you a couple of views, such as 32-bit ints and 16-bit ints and 8-bit ints. And what it doesn't really allow you outside of data view, which is slow, but what it doesn't really allow you is unaligned memory access. You can basically only read things at 16-bit boundaries, 8-bit boundaries, 32-bit boundaries. And what this allows us to do when generating pointer code is to, instead of storing byte addressable addresses inside the pointers, we can store the indices into their respective heaps, into the respective views on the same heap. So instead of scaling the address when we're indexing into the array, we only scale it in LLJS when we're assigning into the pointer. So this lets us save a few operations. We're basically betting on the fact that you're probably going to be accessing memory a lot more than doing pointer mutations between different widths. And Emscripten does this a little differently, whereas they always scale the address when they access. But then since everything is byte addressable, they don't need to scale the addresses when they assign the pointers to each other. This is just the trade-off between what you think your program's going to be doing more. Another nice thing about things like LLJS and Emscripten is that when you compile your code that has machine types, you're generating code that's much more friendly to your JITs than normal JavaScript. Now JITs, including the JavaScript JITs, really like monomorphic code, meaning if your program happens to basically only work on one type ever, your variables are basically monomorphic instead of polymorphic. They can they can optimize much better. And we have higher level information as the LLJS program that this thing is in fact an int, or this thing is in fact a uint, or whatever. And it'd be nice to tell the engine somehow that, we know this for a fact, so you shouldn't emit, say, overflow checks for addition in JavaScript, because in JavaScript we only have one number type. Of course, the engines represent them as either an int32, which eventually overflows to a double or something, but to the JavaScript programmer, there's only one number type, and addition is not closed on the integers, for instance. And it'd be really nice if we can tell the JIT that it is, for this program, closed on the integers, then it can emit more efficient code. So in things like LLJS, we can do things such as compile ints down to all accesses of variables that are declared to be ints with a bitwise or a 0. This has the effect of telling the engine that every use of this variable is truncated to 32-bit ints, and you can just kind of forget about the overflow checks. Among other things, this lets you have more predictable performance, because a JITted language usually have dynamic checks for soundness, and they end up recompiling. Doing this lets you also sometimes get rid of those dynamic checks. All right, so that's basically what we have in the language. Fairly simple in how we compiled them, how we compiled the more interesting bits. This is just some example code for how we might use it. This is a struct of a 4x4 matrix with some accompanying multiplication function that does simple matrix multiplication. But this is not so nice to use. All we have is a struct. So maybe we can write a thin wrapper that has one field, which basically makes the new struct, and then use some casts here and there to call the multiplication method that we defined, so we end up having a more JavaScript-y interface. Note that we actually manually cast this.m and other.m back to capital M star, because once we're in JavaScript land, the types are gone. The type system is simply not strong enough. We don't want it to be strong enough to be able to somehow infer that this.m and other.m are in fact M stars. So here you have to write some manual interfacing code. But then this leads to the question, now that you're manually managing memory, you can have memory leaks. So what do? Well, maybe you can have a free function, which then calls the delete operator, which then actually frees the memory you allocated in the heap. But we can't do that either. Well, we can, but you have to do this manually. It'd be nice if we had some language level support, but we're no longer relying on the GC. If the language could expose finalizers, then we can do this. But we can't expose finalizers for reasons of not exposing GC state. Or if I have weak references, it'd be nice if we could do that too, but we don't have weak references either. With weak references, we can tell if something is about to be collected, much as with finalizers. So now we have, but we've gone through this before with C, with all the memory problems and the double freeze and the not remembering to free. Over the summer, one of our interns, Tim Disney of Sweet.js fame, if you haven't checked out his macros work, you really should. He worked briefly, he wrote this in like 2 weeks or something. Since now the heap is a JavaScript object and so easily instrumentable, he basically wrote the equivalent of Algorand-like tool for LLJS, which then detects these things. That's really cool. Another interesting property of something like LLJS is that since it is not dependent on the entire C and C++ toolchain, it seems like it should have better interoperability with JavaScript. But we cannot yet store JS object in the LLJS heap, because typed arrays only take basically those machine types, and they do not take any arbitrary object. We have a couple ideas on how we might do this. Maybe we can have an object ID mapping when we need to store an object. Maybe we can have a shadow heap that only stores object, that is not a typed array, a shadow heap of a normal JavaScript array. But it's in the works, and yeah, but interop is basically pretty hard. So some general concluding remarks. This is kind of crazy, as the tweets have shown, but it's not a general purpose tool. We're not asking you to please write all your JS this way. That's asking you to go back to like the 1960s. So, but if you have a few bits of code in your little game or whatever application you're working on that really needs that memory compactness, that actually lets you write real data structures that have higher structural overhead. If you have like prefix trees with a lot of links with very little data per node, that's going to kill you when you allocate a ton of little objects in JavaScript. This lets you get around that. And if you really miss, assembly and stuff, and you're not lucky enough to work on the jet engines, this gets you back in touch with the bits and bytes. So the status of this project right now is that we have a research prototype, which really is just a nicer way of saying it's really buggy. But it works for the most part. We have a nice, if you have Node installed, it has a command line compiler that you can use. It ships with the KNR malloc implementation, which is probably not the malloc you want, but it works. We have at least 2 users, me and Michael, but apparently this was made known to us via Twitter the other day. So we wrote this entire language so you can have manual memory management, so you can have compact, nice efficient code, and the first thing that someone writes and publicly tweets is a mark and sweep GC. It's quite amazing. All right. Thank you for listening. Happy to take any questions. Yes. Was that right?
What hoops?
So right now
Oh, yeah.
oh, sorry. The question was if I want to write part of my program in normal JavaScript and another little part of my program in LLJS, what hoops do I have to jump through to get them to work together? Right now, the command line compiler generates the module pattern around your LLJS code, which then is just normal JavaScript code. The problem is the types are erased in the generated JavaScript code. So you have to basically have a little exports file that you write yourself to preserve the types when you need to use it from elsewhere. Like in the matrix example that we showed, in the .prototype.mol function, when you get this .m out, you don't know that it's an m star, and you have to basically cast it back. But otherwise, we just generate normal JavaScript functions, so you can just call it. It's parameterized around the typed array heap, and you can choose how big you want that to be when you generate the code. Yeah. Next question, please. Yes.
What does the code actually compile when I do memory management? For example, when I malloc or free something, is it just to make sure that I got it right? You have implemented your own heap, which is a typed array, and there are all the memory operations performed on, right?
Yeah. So it's essentially keeping a free list internally. So every allocate, when you send new, it just finds the next free list node, and then it gives you it has to put the malloc header in front, right? So it's like our implementation malloc in LLJS.
And another question regarding the alignment of arrays you talked about. What happens when can you go back to the the alignment slide? When I take let's say the X array, which is an I32 array, and cast it to an I16 array, then I can access unaligned memory, right?
No.
No.
So you're talking about casting a pointer, or
Yeah, right. Then I can.
You can never cat, because basically when we shift over to scale the pointer addresses, then you basically just lose the precision. So.
What about union? What if you have 2 pointers union on top of each
Right.
other? Don't you get in trouble?
2 pointers union on top of each other.
They basically have to be aligned to the widest. Always.
Right. That would be. I guess that would be a problem.
So you have an I8 pointer and an I16
Right.
pointer union together, and you treat one as one and one as the other, and all of a sudden you're here or there.
Right. That would be a problem. We can fix that. We'll just put them different places.
Research prototypes.
Okay.
Yes. Other questions?
Yeah. Actually, just a minute ago, I realized that if someone throws an exception, we don't do anything about the stack pointer to fix it.
Oh.
Yeah.
Oh.
So
Yeah, okay, question. Pointer arithmetic, do you have a slide for that or examples? Is it even
no.
necessary? Or,
If you want
would
to,
you want to do that?
Yeah,
in
if you're used to
LLJS?
writing your array traversal code using bumping pointers instead of using an index, you can do that. It's fine. It's the generated code is not too bad to read either, because there you're not kind of crossing this alignment boundary. You're just bumping a pointer of the same alignment. So it's actually just a bump in an increment in the generated JavaScript code also. It's not too bad. Of course, the rest of the code is going to be hard to read because it's all going to be accessing to the memory.
So what lessons are you going to take from this, if any, and put them in normal SpiderMonkey?
what do you mean, the features language, or
No, but
what can we?
how can you make SpiderMonkey faster? You seem like some of the original examples in some
Well,
cases, you do know the types.
Yeah,
and
you can
could-
always do things like tricks, right? You can say you can do pattern matching on like the kinds of code that you generate. And then you can say, oh, for this particular pattern, I can like have a fast optimization, like the example with over zero.
Yeah, I think with Mscripten especially, it's driven in the new SpiderMonkey JIT in IonMonkey. There's analysis to look for bitwise operations and things that truncate to 32 bits, and omit overflow checks and boxing and stuff like that.
So we should be doing lots of bitwise operations and so on, and you know,
I mean,
shifting by 2 instead of dividing by 8 and things like that.
I'm going to say no, because that's going to make your code look a lot worse. If you want to do that as like an extra build pass, feel free. But like, you know, it seems bad to have the programmer to jump through hoops to optimize for a specific JIT. It seems like a horrible idea.
So you talked about the memory overhead and just vanilla JavaScript objects. I'm curious if there's a crossover point where the cost of your malloc and free implemented in JavaScript becomes higher than the cost of memory allocations and garbage collections that are implemented in C++, probably typically in most of the engines. Do you have any data on that? Like, in other words, how much random allocation and freeing would I have to do for the overhead of the regular objects to actually be smaller than the overhead of the allocation and freeing that you guys have to do manually in JavaScript?
Well, I don't think it's necessarily a matter of like, because I mean the GCs are really, really fast, right? So it's not about that in particular. It's that you don't have any GC pauses. So even if it's about the same speed, it will be sort of a smoother
So
curve.
we really are talking primarily about pauses. So if we,
Yeah.
like, if inside the engines we got the pauses down to negligible speed, we will be basically on par with the goals that you're trying to accomplish.
Yeah.
Is that accurate?
But I think it'd be hard to keep it sort of consistent speed. I mean,
Sometimes, like, you want to control exactly, if you're drawing frames, maybe you want to trigger GC exactly at this point in time so that your animation looks a little bit smoother. Even if you get your GC to be extremely fast, it's unlikely that they'll expose that level of control, right?
I mean, you can always just do like region allocation schemes, so you can do your own malloc. You just wipe out the whole thing when you're done with it. So.
Sorry, didn't you see that this code looks more like C code than JavaScript code? And in this case, I think more efficient write code in the C++ and use Node.js model right in the C++. No?
Can you repeat that? What?
You make write your models for Node.js on the clean C++, and didn't you think that its variant will be more effective than this? No?
You're talking about like actually writing in C++ modules and then having bindings to well, I mean, certainly that's much more efficient than Node.js, but if you want to run on the browser or something.
I didn't see benefits from this variant from their variant.
But they run. So
Are
I mean,
you
it's
talking
actually running native code, right?
Yeah, are you talking about writing a native code and then writing and using some foreign function interface to use it inside Node, or I'm not familiar with what exactly you're asking with the Node stuff. Oh.
For Node.js, I mean, I think you're better off just writing, writing in C, right? But if you need it to run in the browser. Right.
Right. This is, I mean, the compilers in JavaScript. If you really want, you can bundle the compiler on your page and whatever. The rest of the things, the nice things you get with all JavaScript solutions.
Great. Okay, so I think that's it for this. Thank you very much, Shu and Michael.
Thank you.